Okay, so for this, we want to use the data from the textbook to determine the bond lengths. Now, what we're considering, or what we're assuming, is that get this right, these atoms in this bond are spheres, and that when they bond, it's just the spheres coming together, touching, like you would two pool balls on a pool table would just click together. And then since we know the atomic radii, that's been tabulated, then the bond length just equals the radius of atom 1 plus the radius of atom 2. In this case, they're both the same. So we have, look at the table, and they have hydrogen. Now here's the thing, they give the hydrogen as 37 pm, picometer. So that means that between the two of them, so the distance from here to here, the radius of one of these hydrogen atoms is 37 picometers. So the bond length is 74 picometers, and that's fine by me if you want to leave it as that. If they get large enough, you might change over to nanometers, but in this case, that's as far as we need to go. So we have fluorine. So again, we have fluorines. We have two atoms stuck together. Fluorines are 64 picometers. So so if we want to go from one nucleus to the other, that's the bond length. It's not the full size of the atom, but just the distance between the nuclei. Then it's going to be 2 times 64, or 128 picometers. Then CF. We look at CF here. So for carbon, there's no need to write this full thing out. You can just say this is 77 picometers. Fluorine is 64, and then just add them up. So 77, 64, so 141 picometers. The thing is that this is about as simple of a problem as we have we'll have on the exam. So don't mess it up by overthinking it. What happens a lot of times, I almost hate to say this because this is the thing that students do. So but it's better to say it. I think they'll add them up and then they'll divide by 2. What they found is the average bond length. Then that's or the average atomic radius, I should say. They haven't found the bond length. So when you add them up, stop. And it's really depressing when somebody gets 128 and then they divide by 2. And I have to take points on it. I have to, because that's not the bond length. So just stop there. You're not trying to find the average. It seems like there's something else to be done here. There isn't. Very straightforward, very simple. We just find the atomic radius of hydrogen, the atomic radius of oxygen. Those will be given. You definitely don't have to memorize those. You'll be given those. This is 103 picometers. That's it. That's as far as you go. Okay, now, bond, so we had bond length, then bond order. We'll draw methane. Let me just draw out these molecules. Then we had sulfuric acid. And I'll put in the dots. You don't have to for this one. And then acetylene. So is this C2H2? So they asked for the bond order. A single bond is a bond order of 1, which is BO. It's unfortunate, but that bond order BO equals 2, and triple, the bond order is 3. Now, when students see this first time, just like the bond length, it's so ridiculously simple that it seems like, and especially in this case, like, well, why even bother to rename it? Well, because what we'll see later when we're studying in chapter 10, they talk about bond orders of 1.5 or 2.5. fractions. So you can actually have a fraction of a bond. It gets very tricky, very complex in the higher levels of chemistry. And you'll need to have a bond order because you can't say you have a single bond. You might have a 1.33 bond, where which what it means is that there's one electron being shared between 3 atoms. So it can get tricky. So it's not just we're not just doing this to add workload here. Bond order is very important, but here it's going to be very simple. So they want to know the bond order. So just BO equals 1, 1, 1, and 1. This is 1, 1, and then 2, 2, and the others would be 1. And then this one would be 1, 1, and 3. And since, on the exam just to make sure that everything's clear, you'd put BO equal to 3, BO equal to 1, BO equal to 1. And then the last thing here, so that's it. That's all you need to do for that one at this point. Just be aware that there is that idea of the bond order. Determine the enthalpy of the following reaction using bond energies from your textbook. So what we're going to do, it's pretty clever, and it works out pretty well too. Just draw out all the molecules. There's 2 oxygens, so draw them both out. I'm going to be complete with the dots. Then we have CO2. There's only one of these. And then we have 2 waters. I'm just going to draw them flat, even though I know these are bent. We'll see that in the next chapter. So if we draw these structures, what they're saying is that if you know the bond energy, the energy that will break this bond, then it'll be the same for each of these. And if what we do is we break every single one of these bonds, it will require a certain amount of energy. If we know how much energy it requires to break the double bond between the oxygens, then it must be twice as much to break the bonds for 2 oxygens. If we know how much energy it takes to break this bond, then it should be 4 times as much to break them up. And then we just break them all up into their atoms. And then when they get pulled back together, there's a release of energy. That's when the energy is released. We put energy in here to break the bonds, and then when they reform, the same amount of energy is given off, or an amount of energy is given off to allow them to form. So here we're going to break up the bonds. Here we form them, but we can figure out how much energy is in each of them from the table. Now the table shows that between carbon and hydrogen, a carbon-hydrogen bond, there is it takes 411 kilojoules of energy per mole to break them. And we're going to have 4 of these, so it'll be 4 times this. And that's it. And then we've broken them up into their atoms. Oxygen, if you look, it's oxygen a double bond to oxygen. The multiple bonds are found at the bottom of the table. And there's 2 of them, and it's 2 times 494. So you should be able to find the table, or the information from the table. And then we have carbon dioxide. Now this is a little tricky. You have C double bonded to oxygen, and it says 745, but then it says 799 in CO2. So each of these is 799 kilojoules per mole. CO2 just happens to be a very, very stable molecule. So on this side we have 2 times 799. And I'm going to leave off the kilojoules per mole just so it doesn't look too messy. And then we are going to form 1, 2, 3, 4. So this is C double bonded to O. We're going to have and times 2, so 4 times OH, and OH is 4 times 459 on this side. So what you do is figure out how much energy you needed to pull the molecules apart on the one side, so it's 4 times 411 plus 494 plus, and I get 2,632 kilojoules per mole worth of energy to break the bonds. That's the amount of energy that went into it. So let me try this one more time. On this side we have let's see, so 15, that makes sense, and then 4 times 4. We have 3434 kilojoules per mole that went in. Now remember our exothermic versus endothermic, where the energy goes in or it comes out, we'll be able to tell by the sign. Well, we had to put energy in here, so this be positive, and this energy was released, so this is negative. So if we want to determine what the enthalpy is, we take the 3,434 minus plus the 2,632. So this is the energy that was released, so it went out of the system, that's negative. To break these bonds, it was positive, so 3,434 minus 2,632. And this comes up to be minus 802 kilojoules per mole. And that's our delta H. So figure out, you can just think of it as what energy does it take to break all the bonds on this side? What does it take to break all the bonds on this side? Even though you're forming them here, just get your numbers. The product side will always be negative because that'll be the energy that's released. The reactant side will be positive because you had to put the energy in, and then just take that negative number plus this positive number, and that's your delta H.